right, good afternoon, and welcome to all of you to another session of the joint MTL seminar with the MIT AI hardware program. My name is Jesus del Amo, and I'm a professor of electrical engineering. Today, we're really lucky to have the visit of Dr. Timothy Brunner, who will give a talk titled Research to Improve Image Contrast in EUV, Extreme UV Lithography. EUV has and will continue to be a critical technology for the future advancement of Moore's law, and ASML is undisputably the world leader in this area. We are actually delighted to have ASML as a member of the AI hardware program at MIT. Dr. Brunner is a director at ASML. He's with ASML Technology Development Center in Ridgefield, Connecticut. He received a BA in physics from Carleton University and a PhD in physics from MIT. And he's devoted his entire career to optical lithography in various companies, Perkin & Elmer, Xerox PARC, IBM Research, Global Foundries, and more recently at ASML. And his work has earned him many accolades. Among them, he is an SPIE Fellow, and he also was awarded the Fritz Zernike Award for microlithography by the SPIE also. Tim, it's a real pleasure to have you with us today. Thank you very much.
Thank you so much. All right. Well, I'm really happy to be here. This is kind of giving some span of lithography. Hank has contributed mightily to pretty much all of these steps and so on, and I've worked in it too. This is a 40-year span. I actually was at MIT in 1975 to 1980. I wasn't doing lithography, I was doing physics. But my career in lithography started in 1980, so 5 years to the left of the lowest point. So where it says resolution, 1,000 nanometers, when I started, it was around 2,500 nanometer resolution when I began at Perkin Elmer, and it was with a mercury arc light source called G-line, 436 nanometers. It was a color you could see with your eyeball. It looked blue. Now we've progressed down step by step by step. You cannot see the radiation any longer. But each of these points in the curve is a major exposure tool that would be a tool for, first of all, Perkin Elmer, and then GCA, and then ASML started coming in the 1990 timeframe, and then started using lasers, krypton fluoride, then argon fluoride, and then the wonderful idea of using immersion to get even shorter wavelength because of refractive index of water. And I'll be talking about this EUV wavelength. And first, before we get into that, what is the thrust of going down in resolution? Well, we're trying to support Moore's law, so we need to be smaller devices, meaning faster, most importantly, cheaper, so that you could use economy of scale and so on. And the key equation guiding lithographers is called the Rayleigh equation, this CD equal K1 lambda divided by NA. Lambda is the wavelength of the radiation. So that's highlighted going from 365 nanometers down to 13.5 nanometers. And maybe we'll go further. Hank was just telling me about some ideas he's thinking about for going beyond that. But this is kind of the current roadmap and span. And then NA is another thing. Obviously, you want to reduce lambda because you're trying to get the smallest possible critical dimension printed. So NA for EUV is currently at 0.33 NA, and you're able to get into 15 nanometer critical dimensions. But by pushing the NA into 0.55 territory, we're going to get into sub 10 nanometer critical dimensions in the very near future. And yeah, and then this K1 is kind of a lithographer's constant of how challenging things are. And K1 can be as low as 0.25 if you have a very well-developed process, if your resist is very good, if your mask is very good, and so on. So to realize low K1 means that every part of the lithography system has to work. So what I'd like to go over is briefly a status of EUV lithography, then a really fundamental thing, which is stochastic noise in EUV. And I want to show you, I hope I can give a feel for what that stochastic noise is, how we overcome it with very high image contrast. And then a lot of my talk is kind of a specialist kind of thing of how do you improve image contrast. I hope I can at least give you a glimmer of how we're trying to do that and how we've achieved higher contrast. So EUV lithography in the last several years has gone from really a research activity into a mainstream activity. And that curve here is showing the accumulated number of wafers made by EUV. And by the way, this is stopping at the end of 2022. It continues to shoot up. So, you know, it's hundreds of millions of 300 millimeter wafers have been patterned with this technology. It is not a research subject any longer. And from our point of view, we're selling every quarter, you know, let's say a dozen machines or something. They're very expensive machines, so that keeps our business going. And Moore's Law has two pieces. One piece is making things small and good and precise so that the devices that are made by this are very, very capable. But the other piece that's equally important, absolutely as important economically, is that we make it fast. And by making it fast, you can take a $100 million machine, and if you spit out enough wafers per hour, you can make that an economical thing to supply an industry. So the throughput is very, very important, and it's the EUV power that is driving that. In the next few years, we're going to be moving to 1,000 watts of EUV power, which like 10 years ago was, I would say, almost unimaginable. And how do we take steps to do that? Well, this is showing this green step, this blue step, and this red step. I'm going to tell you about pre-pulse in the next slide, but these are three methods to increase the power of EUV. And the rep rate scaling is something you'll readily understand, which is currently our sources use 50,000 pulses of CO2 laser onto a tin droplet to make the EUV. So brute force, we go to 100,000 pulses per second, and we get twice the power on the average. So that's one step we're taking, which is the blue indicator, blue arrow. We're also using bigger and bigger CO2 lasers. So this is the kind of thing you have to think through and look for something which can supply the power needed to put down all the power that's needed. Now, this is a really, really cool thing. And what you're seeing is that in time, there is a droplet of tin that spews out into a vacuum chamber. And then that droplet of tin goes into a pre-pulse. The pre-pulse purpose is to go from this spherical drop to a disk, a thin disk. Because once you have this thin disk, now you're kind of ideally ready to blast it away with high efficiency. So that's the main pulse, which is a second pulse. So these 50,000 droplets a second, twice is hit precisely. So it's just an amazing technological thing.
The droplets are coming at 50,000?
Yes, yes.
50,000 droplets? How big is the droplet?
Like 15 microns, 20 micron. so very, very small droplets, not a lot of material to it. But I always thought of this as a PhD thesis that you would never be able to industrialize. That's the way I thought about it 15 years ago, before I joined ASML. Now I've seen the light, and I know that this is, tremendously industrialized, repeatable, reliable economic process. But, 15 years ago, that was not the case. This was just what seemed to me kind of an unlikely approach. So the status of EUV, just to summarize, is that all the chip makers that you know, Apple, TSMC, everybody uses EUV for the most advanced products. We have this platform called NXE. That's a 0.33 NA, or what we call the low NA EUV system, a platform, and it does everything that needs to be done. It transports the reticle. It puts wafers in. It aligns them. It does all the things needed, and these things are constantly updating and evolving into improved overlay error, improved throughput, improved uptime, which our customers are driving us towards. And we continue to make strong progress in that. Another thing I'll just briefly mention is energy efficiency. This is really important because these CO2 lasers are monstrous things. So if you can go from 7% efficiency to 7.3% efficiency, it makes a big economic difference. And then in the near future, we're going to have a revolutionary 0.55 NA system, and that's under intense development right now. There are tools at Intel and at IMEC, and yeah, it will be developed in the next several years and give new capability. And this is what Moore's Law drives us to do. We have to make things smaller. We have to make them faster. Okay.
You mentioned EPE, what is that?
Edge placement error. I apologize for making acronyms, but in this game, I've been in the game of lithography for, like 45 years, and I know a lot of acronyms, and you don't, and so I've tried to reduce the number, but EPE is edge placement error. It's overlay error and CD control, edge placement. So I want to talk about image contrast, so let's first define that. It's this ratio of the maximum of the image, I max, the minimum of the image, I min, and that ratio. So if it's ideal and you have a certain intensity at the peak and you have 0 at the minimum, then you get that ratio to be 100% contrast. That's highly desirable for your dark portions of the image to be near 0. It's highly desirable. And I'll show some evidence for that. But there's something that goes on, which is we control the image that is the patterns of light, and that's what we sell at ASML. But that's not what counts. What counts is what's in the resist. And inside the resist, there are all kinds of blurring mechanisms that will take that crisp image that I'm showing in black here, and it will blur it because, for example, if you're using a chemically amplified resist, you create an acid with the photons, and then the acid drives a catalysis process, and when you drive that process, it moves around a little bit, so there's a blur. So what really counts is this dashed thing, which I'm calling the effective image, what happens inside the resist. That's the thing that really counts. That's what we're trying to maximize. And now I'm trying to make the argument that contrast can reduce stochastic errors. In a moment, in a couple slides, I'm going to show what stochastic errors are. But what this is showing is that a very important metric called local CD uniformity, which is the variation in the dimension that you print, depends on 1 over the contrast. So if you improve the contrast by a factor of 2, then you're making the LCDU a factor of 2 less. Now, another way of doing it is to spend more dose, throw more numbers of photons at it. And this is kind of a shot noise argument, and we actually see it in practice, is that when you increase the dose, you can reduce the stochastic noise, and it goes by about 1 over the square root of dose. This is extraordinarily expensive, and our customers hate us when we suggest that, oh, this is one way of reducing the noise, the stochastic noise, because that means that instead of 100 wafers an hour, or let's say 200 wafers an hour, if you need twice the dose, then you can only do 100 wafers an hour. So the economics gets very bad. So it is far more economically desirable to increase the contrast than to increase the dose. Now I want to, the fundamentals of stochastic noise. Probably many of you are familiar with this, but when you send light and make a pattern, it's not a smooth continuing thing. Like your image simulation program will say, oh, this is my image. It's this nice Gaussian shape. No, never, never, ever. Because photons come one at a time. So when you have the high intensity, there's a lot of, think of it like a shotgun. Boink, 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 boink. There's a high density of shotgun shells here. There's a low density here. And so you end up inside the resist with some peppering of the actual photons. And then when you develop it out and you do the processing of the resist, you get something, and it invariably has this rough, line edge roughness that we seek to minimize. And here I'm showing an example. Maybe it's slightly easier to see. This is with a contact hole. That is a kind of a circular, two-dimensional object that you're trying to make. And if you have a low-dose resist, which is highly desirable for throughput, you really want to have a 30 millijoule per centimeter squared resist process so that you can put lots of wafers through the machine. But if you go ahead and look for that dose, where are the photons? Well, there they are. You know, you can count each photon, you can touch them. And it's a stochastic process. So every time you do a new contact hole, it's a different stochastic pattern governed by this probability density in the image here. So if you want to make it a smoother thing, go for a higher dose. It's the same aerial image, exactly the same image profile. But now there's enough statistics there that, oh, that's beginning to look like kind of a circular contact hole, which is what I am trying to print. So let's say you're trying to do a chip, and you've got to put 5 billion contact holes down. Well, you need very high probability statistics. You know, if you make 1 in a million of these 5 billion wrong, then you're going to have 5,000 errors on your chip, and that's not going to fly. You've got to make an error-free chip. So here I'm showing an example of something where on the photo mask, there is an endless sea of contact holes. But when we looked at this one place on the wafer, oh, it's missing. And if we looked at a repetition, the same mask printed on another wafer, that's not there. This is a stochastic defect. It's like a 1 in a billion type thing. And we've done experiments where we look at the distribution of CDs of, in this case, 50 million contact holes were measured, and you're seeing the distribution of the CD. It was targeted at 25 nanometer CD, and what you may be familiar with for a lot of yield analysis, you talk about Six Sigma statistics, for example, and you think in your mind, Gaussian, Gaussian. When we actually measure these distributions, you can see with your eye, the black is an ideal Gaussian fit, which is always symmetric, right, around the mean. But when we look at our actual distribution, what we see is there are these tails, and the tails are only on one side of the distribution. And it's kind of unfortunate that it's on the side where it's small, and in fact, there was a missing contact. That was the picture. That was the SEM I showed you. There was actually a missing contact hole. So that's now the CD dimension isn't capturing everything going on because there can be a defect where there's a missing feature. But yeah, if you have some characteristic of a device and it depends on hitting some very narrow window, the fact that this is asymmetric is a big problem. And especially if you die on the small side and you don't die so much on the large side. So this is a reality of stochastic noise in lithography. So now I'm going to tell you about image contrast. And the way I think about it, it's kind of simple-minded, the way I learned to think at MIT. So I was doing atomic physics, and you don't want to think about lots of atoms. You want to think about one atom and one photon. That's what you want to do your theory on. We think we can understand that. But here I'm boiling down an imaging thing into the simplest imaging, which is just to take two plane waves and interfere them, and you'll get a sinusoidal fringe pattern. And if everything is ideal and the polarization is right, everything is ideal, then it will go to 0 in the fringes, and you'll get perfect contrast. Now, what can kill contrast? Many, many factors. I'm not going to go through them all, but each of these factors can reduce the contrast. Somebody asked this morning about our mechanical systems in ASML and whether they're sensitive to vibration. Yes, very, very, very sensitive. And there's a term in the contrast, MSD stands for moving stage deviation. It means that if there's wiggling, that crisp image you have is blurred out by that. So we have a term for that. And for most of the machines we make, for non-defective machines, that term is 1. We don't see any contribution from our machine as it's normally functioning. But that takes a tremendous amount of work to achieve. But now I'll tell you about the things that are still present in our machines, even though our machines are functioning perfectly. The first thing is the resist blur, which is that in the resist process, you put in, let's say, a Dirac delta of a perfect image, right? And then the process will always blur it out, and there's no avoiding it. There are different processes to choose from, and you can find lower blur processes, but it's always present. Another one that I'm going to spend more time on is this pole-to-pole image fading. It doesn't probably make sense, but try to remember that. I'm going to be showing you a picture of what this pole-to-pole fading is, and I hope it will be meaningful to you. So now looking at all these many factors I showed you all, I'm picking out the factors which we find to be practically important, the ones that most differ from one. They're the ones that make the most sense to pay attention to and try to tackle. So this pole-to-pole in yellow, that's what a lot of this talk, the final bit of the talk will be about. So I've been talking about high contrast, and it's desirable to have high contrast. How do you measure contrast? What you have to do is what's called a focus exposure matrix wafer, which is a wafer where in this direction you change the focus, and in this direction you change the exposure, and you measure many, many, many line widths. as the focus and exposure changes. And you draw out this curve. It's usually called a bossing curve after my old colleague at PerkinElmer, John Bossing, who first did these diagrams. And basically, by analyzing all that data, you can come out with a number for what the contrast is with a suitable analysis. But you have to do hundreds of SEM measurements, which is time-consuming and expensive. But this is established infrastructure all over the world. And there's one other problem with it, which is that after you've measured all across this wafer and everything, you get one value of contrast. Well, what if the contrast is varying across the wafer? Well, you can't see that because you've gotten this averaged quantity. So what we developed with our collaborators at IMEC is a new way of measuring contrast that's using something called the mask error enhancement factor. And it sounds like a mouthful, but it's a pretty easy concept. The concept is that we have a certain test pattern, and the test pattern is, for example, 40 nanometer pitch. That means that from center to center, the lines are 40 nanometers apart. And so if it's 1-to-1, then it would be a 20 nanometer line and a 20 nanometer space. But we have a test pattern where there are 5 different widths in the test pattern. And then we can measure those 5 different test patterns as they're printed on the wafer and measure the CD and of the printed wafer. And what we find is that typically that slope is not 1. In other words, let's say you made the 20 hit 20. Then when you do 19, it's not printing 19. It's printing like 18.4 or something like that. And what you can do with experimental data is you can measure this test pattern, measure this slope, and then from that slope, you can say something about the contrast. There's a theory about it in this paper. I'm not going to get into that. But anyway, the beauty of this is you can put these MEF test patterns all across the wafer. So you can look all across the wafer in your process, which, you know, this may be a $10 billion fab, and you may have invested $100 million on one tool, and you need it to be good, right? So here you can use this method to measure all across the wafer and ensure that the contrast is under good control. So with this MEF method of measuring the contrast, we've done some experiments at IMEC in which we wanted to look at some of these important factors in changing the overall contrast. Remember, I told you the resist contrast is an important part of the problem. So here we used 3 different resists. We used kind of the standard chemically amplified resist process that was, I'll say it's the standard at IMEC at the time. And then, we measured the contrast using this MEF method.
How thick is the resist, and are you using a multi-layer?
No, it's a single layer resist. Well, it's a single layer resist with a special coating on the bottom. But yeah, it's a single layer. It's about 30 nanometers thick.
So the resist is 30 nanometers thick?
Yeah.
And you use that to transfer patterns?
Well, in this experiment, we're not transferring pattern. We're just measuring the resist. Yeah. But
when you transfer patterns, you're not using 35 nanometers of resist.
Sometimes we are. But you're right that in a practical patterning of a real device, you would use a multi-layer process. You would have the key resist, which is the part I'm paying my attention to here, but then you would use that pattern of, say, 30 nanometers of an organic thing to maybe translate into a titanium nitride hard mask, or, you know, you would have all the dry etch clever schemes that people use. But in this experiment, we were just using a single layer resist. So, and we measured the contrast as a function of focus. We had different parts of the wafer with different focus. And we saw, just like we expected theoretically, the contrast is the highest at the best focus. And then we changed to a different resist. Oh, that CAR plus process, that's a superior contrast. So the blur is lower in that particular resist. And now we had a way of quantifying that. And then finally, we went to the latest, greatest resist process being used right now is called a metal oxide resist, which is a very different concept than a chemically amplified resist. Sorry, I won't have time to go into that concept. But anyway, this metal oxide resist has much better contrast, much lower blur. So we were able to see that clearly with this MEF method of measuring contrast. Another thing we did was we changed, yeah, I'm sorry, I'm not going to get a chance to fully describe this, but we have these shapes, pupil shapes, which describe how the EUV light goes onto the mask. At the center of that circle, it would be coming right down normal incidence. And on this side, it means that the source ray that goes on the mask is tilted so that it goes to the edge of the numerical aperture. So anyway, all these things are 3 different source shapes. And without going into a lot of detail, using source shape to optimize contrast is a well-established thing in EUV lithography. And we're always trying to figure out how to do it better. Well, here we use our contrast method. And first of all, we do simulations and say, oh, what should the contrast through focus curve look like for these 3 illumination shapes? And then we did our experiments, and we were pleased to see that there was pretty reasonable qualitative resemblance to that shape. So indeed, the orange, the dipole source shape, is the optimum for contrast. Okay, now I'm going to get into this contrast lost from fading. Yeah, again, the source shape is very important. What I'm showing here is what we call a dipole. So there's a left pole and a right pole in that shape. And when you image this in our tool, you get an aerial image shape that has this kind of contrast. But now, let's say I'm going to divide up the dipole into its 2 major pieces. There's a left side and a right side. Here I'm showing the right side. Oh, that is an image with higher contrast than the dipole, because that was 76% contrast. But if I just use one pole, oh, it's 89% contrast. Interesting. Maybe there's something we can do here. And but I think your eye's probably noticing that there's like a shift of that image. It's no longer centered. Now let's do it with the other monopole in green, and that's the left monopole. Notice you have another high resolution, high contrast image, but they're shifted. The reason why the dipole has less contrast is because those 2 shifted things, when you add them up, have lower contrast. So now I want to say something about masks, just briefly what the structure of the mask is. It consists of these amazing multi-layers made of alternate layers of molybdenum and silicon. And they are configured. So you get about, I don't know, 0.4% reflection from each of these surfaces. But by adding them up coherently, you can get a 65% reflection. This enables EUV lithography, this idea, and that's built into the mask too. So these multi-layers are present in every one of our imaging mirrors on our machines, but also in the mask. And and then what I want to show also is this non-ideal aspect, what we were just talking about, Hank, that the only way that you can get the light onto the mask is obliquely. And the reason is because if you just were to normally put it on the mask and then come back, then this pupil would block the projection optics. Now there are ways around that, and that may be worth exploring at some point, but this is what everybody uses in the EUV world at the present moment. And so by coming at this oblique angle, and then the projection optic collecting light on the other side, we have an asymmetry, and that is where this shift comes from. It's kind of mysterious, I didn't explain. Well, why is that shift coming about that causes this image contrast loss? And this is a calculation on the mask itself. Here's the absorber of the mask. The multi-layer is here. Light is coming down like this. And I'm showing two images. This is the left monopole where the image comes from, or the source comes from the left. And when you do that, this casts a huge shadow here. And it's an asymmetric shadow. This is lost on a lot of people's discussion of mask shadowing. It's not just a throughput thing. It changes the symmetry in the overlay. And yeah, so this is showing, yeah, this is the electromagnetic wave going down into the multilayer. This is the part that counts. This is reflecting back. This is the part that goes into the imaging system. And you can see that the left pole is shifted one way, the right pole is shifted the other way. So this is the fundamental physics that we have to deal with. So what can you do about that? So here's a summary showing the left pole and the right pole and the dipole summation of that. What if you did this? What if I took this red multipole, monopole, and I shift it so it's right perfectly centered? Because I've got a wafer sitting on a beautiful stage that I can control to nanometer position, right? And what if I then do a second exposure where I take this green sub-image and I shift it exactly on top of each other? Now there's no fading. There's no loss of contrast. And so this is a technique we've been calling dual monopole. And the solid is showing the normal dipole image that is what is in production today. And the dashed, the dashed is the normal. The solid is showing the dual monopole, how much more contrast you get. That seems like it's not much. They're so similar. No, because there's twice as much light in this. So the stochastic noise degradation is very significant. I'll show you some data. I don't want to show this part. So we did some experiments. And the way we did our experiments is we used the flexibility of our tool to do these separate exposures of the right monopole and the left monopole. And then we manually would shift relatively those two sub-exposures. And so we're looking to experimentally find at what program shift do we get the maximum contrast. And we have this way of measuring image contrast with the MEF targets. And these are experimental data points. The blue and the white were two separate wafers. And so what we were able to do is a couple interesting things came out of this. One is that the points that we saw, the blue and the white points, were in agreement that the best shift for the dual monopole was 5.06 nanometers. And we're very proud of that number. It's a very precise number. This is the kind of thing that RLE physicists do in Building 26. So I'm very happy with this number. But the other thing is we saw that the image contrast, which is so important for the practical performance of the lithography, was increased by fully 18% when we found the optimum shift. So now I'm going to show you some of the practical things that, were exciting to use this dual monopole higher contrast imaging. Many times you're doing some structure for a device, and there'll be an array of devices, and one of the things that people hate is line shortening, and the tip-to-tip is a commonly used metric for kind of quality. How close can I make those things? Oh, I really want them to almost touch because I want the highest density, but oh, damn, they never do. When I try to make them close, they print so that they're larger gaps. So if we do ordinary dipole, we get a gap of about 25 nanometers. When we do this dual monopole, we got a 3 nanometer gap. Some designers are finding this very interesting because it can be about a 10% shrink in the two-dimensional density of their circuits. So that's what dual monopole can give. Another thing that's sometimes a practical difficulty with EUV lithography is that different types of structures will come to best focus at different best focus offsets. But there's only, when we do the exposure, there's only one setting we can do for the best focus offset. Here I'm showing the best focus that we measured for the normal dipole exposure. And this blue line is showing for pitch 28, so dense lines. And here's for pitch 56, the black dot. And it's about like a 30 nanometer focus shift, which is significant. And then for another pitch, 96, so there's this span of focus occurring for dipole. But if we go to this dual monopole with the best shift, where we saw the best tip-to-tip performance, all 3 of these best focus points were at exactly the same point. So that's very attractive to a process engineer to be able to make all the device features come to the same best focus. Sorry, I've got too much material. Here what I'm showing is a calculation for the shift of the left pole and the right pole. And what you want to do, if the shift is a certain amount, then that's the amount that you want to physically put by moving the wafer, right? But oh no, for different pitches, it's a different shift. So let's do a compromise of about an 8 nanometer shift. And what can we get? And the answer was very significant advantage. So another aspect of stochastic noise is that we get line width roughness. And we're always looking in our processes to get lower and lower line width roughness. Here I'm showing a plot for many different pitches of the line width roughness, where the dipole, that is the normal lithographic mass production method, is shown as black dots, and the dual monopole is shown as open circles. And we've made a significant step down in line width roughness for all of the different pitches. So this is very attractive. And now I can't explain this adequately, but in IMEC, there's a researcher named Peter DeBishop who's come up with a standard method for looking at stochastic defects. And he's looking at failure probability. This is a log scale. And he's showing one type of failure, which is bridges, extra resist going across lines. That's the red. And then the blue is when the line breaks, the resist line breaks. So it's the opposite of a bridge. And what you're trying to do is make valid patterns in this good region here. So he's done many, many experiments and kind of standardized this method. So here we did an experiment where we took a regular dipole exposure. We measured the cliff, the stochastic defect cliff, and then we did the same exposure, except we used a dual monopole exposure. And there are 2 ways of thinking about that. One is, at a fixed level of defect density, we were able to shrink by about a nanometer and make smaller trenches. Or another way of thinking about it is if we leave the CD fixed, then we dropped about a factor of 6 in defect density. So now let's look at that for many different pitches. And we find that for our dual monopole approach, every single pitch we looked at had a significantly lower defect density. And defect density is a very important thing when you're trying to make billions of things. Okay, so to summarize, we see all these patterning advantages with the dual monopole approach. And we think we know why, and we're able to simulate it, and we've demonstrated it experimentally as well. So in summary, we have this method. It's a research method. It is not a production method right now. The reason for that, well, I won't get into the exact, but it's a double exposure technique, right? I had to do exposure of the left pole, and then an exposure of the right pole, so I had to scan the wafer twice. So there are actually ways around this, but not in our current tool. So these are things that we're thinking about for the future, where we might be able to take advantage of this in full high volume production. But we feel happy at this level that the research is panning out and delivering what the simulations said should be there. So with that, I'll close. Thank you for your attention.
All right. Thank you, Tim. We can now take some questions. Yes, please.
Thanks for a very interesting talk. I'm curious how have you characterized how stable the optimal shift of the dual monopole method is? Does it shift over time with like in one chip? Do you have to do it for every wafer? Do you have to do it for every day? I'm curious if that's something you've considered and whether that's a bottleneck to.
Key question, and one that we're trying to get more data on. At the moment, everything we've done is showing stable, but the test pattern we're looking at is at one point in the mask. So another question, very similar to the way you're thinking about it, is across the mask, this large, is that optimum shift changing as you go across the mask? So these experiments are in progress. We don't have the answer to that yet.
Thank you.
There's a consideration of, could you comment on the possibility that some people are looking into of replacing the tin source with a free electron laser?
Yeah, I'm sorry to say that I'm just not expert in it. There's been very serious examination by ASML of free electron sources, and the big research efforts around the world have come to ASML with proposals. So far, there's been nothing compelling us to move forward with that. That could change in the future potentially, but yeah, I mean, I think both of us see some potential advantages of free electron lasers, but I have to say that the practical developments by our San Jose team in making robust industrialized sources is a huge barrier to any new technology.
More questions? Perhaps a question for me. I was asked recently, what comes after high-NA EUV, which is the next generation of technology generation? And I saw on the right corner, on the right bottom corner.
Okay, yeah, let's go back to that slide.
Higher NA EUV.
Yeah,
Can you tell us a little bit about that?
I'll even give you a number for it, which is, we're talking after 0.55 NA. We're beginning to talk about investigations of, you see the number there, 0.75 NA. This is not at all a committed tool by our company yet, but research is beginning on 0.75 NA. And some of the questions are, if we make higher resolution, can the resist grab it, right? Because the resist blurring is always going to be present. So do the resists we know about, are they able to take advantage of, for example, 0.75 NA?
What are the challenges in going from 0.55 to 0.75?
Oh, yeah. I forget the number of 747s it takes to do one of these machines transporting 3, maybe for our low NA tool, maybe 5. Do you have any idea? For high NA, I think it's a bigger machine, so I'm going to guess 5 747s. Anybody want to take a stab?
Potentially 5, but 3 for the low. That I know.
3 for the low, so maybe 5 is a guess for the high. So there are many cost and logistical things to worry about when these things get so big. Another thing, the mirrors themselves grow physically as you get to these higher NAs. And so the interferometers used to optically test them become gigantic. You can drive a bus into these vacuum chambers where our testers is. And they are not trivial low-cost machines. They're not an MIT student setup, right? So those are the kind of practical considerations that come in. Big cost drivers, yeah.
Mm-hmm. Yeah.
In this equation where you have on the board right now, where you have CD equals K1 lambda over NA, K1, the theoretical limit is 0.25, 1 over 4.
Yeah.
So that means that the minimum pitch is 1 over 2 NA, okay?
Correct.
And so you can go through the numbers, you see that the pitches are much, much larger than the so-called critical dimensions.
Absolutely, absolutely.
Yes. So when an industry talks about we're doing 5 nanometer line widths or features, the pitch is much, much larger than that.
Yeah.
So in effect, what happens is that a reactive ion etching process is used to thin the lines down from what the lithography
Yes.
does. Okay. And that's how you get features which are much, much larger than are predicted by this equation. I have a question, actually, which perhaps this would be more appropriate for our monitor here. Is how far can the transistor itself be shifted in terms of how small can the dimensions actually go before the transistor fails?
Yeah, I'm not expert on this. ASML hopes and prays that you device guys can come up with things that allow us to go all the way to 0.75 NA and still make a profitable machine. Yeah.
Mm-hmm. Well, the transistors are moving in the vertical direction by putting sheets, nanosheets on top of each other, so that the pressure to shrink in the lateral dimensions is somehow reduced. But that pressure will continue because eventually the metal is on a plane and has to contact everything. So yeah, it's going to continue to get harder. Any more questions? Yep. Oh, yeah. Maybe we can. Oh, can you read it? Yeah.
So we have a question from one of the Zoom attendees. Does the shift from dual monopole cause increased side lobing or divots in the resist? Are you still able to support addition of SRAFs?
Yes. The answer is yes. We can use, acronyms. I know all the acronyms. I've been at this for like 45 years. SRAF is sub-resolution assist features. That'll be on the test. Hank will test you tomorrow. And yes, dual monopole does not affect that. In fact, we believe that it works more ideally than in the normal imaging process.
All right, any more questions? If not, Tim, thank you very much for a very stimulating talk and for visiting us today.
Good. Thanks for the invitation again.